I want to pick up where I left off last year at my OC3 talk, where I described the different ways of bringing confidential computing to the cloud native level. And there I compared the ways of protecting individual containers and pods compared to protecting entire deployments and clusters. And this year, in this talk, I want to focus on the right-hand side when we talk about entire deployments, entire clusters that should be protected and isolated. But instead of focusing again on this implementation and the internal view, I want to take a different perspective here and look at this from the outset, from the user, from the cloud native way. So if we think about who is using confidential computing in a cloud native sense, last year Mark Russinovich in his keynote said that the early adopters of confidential computing will be the industry that are highly regulated or paranoid. And this makes a lot of sense if you think about finance, public sector, healthcare. But now what we see is with this large movement towards the cloud and also the adoption of Kubernetes on the edge, you can find use cases for protecting your Kubernetes environments, protecting your data in any kind of industry. So it's not about who's using it, what kind of industries are using it, it's about why they're using it and what kind of applications they want to move to certain environments with confidential computing. And what we see here is, of course, compliance is the big driving force. But beyond that, there are also these use cases where confidential computing adds a different scope to Kubernetes, to cloud native security, where you want to isolate and protect yourself against infrastructure-based threats, where you might want to deploy something even on the edge, where you can have no assumptions about the security of your infrastructure and who has access to that. And one case I want to pick out in particular is like SaaS services, where you want to provide or consume a software as a service, and you need to make sure that you're completely, as a provider, need to be sure completely isolated from the data that's provided to you by your customers. And as a customer, you can have guarantees on who has access to your data. So these are the use cases. So now the question is, what kind of requirements do we derive from that to develop software, to develop infrastructure that you can just go ahead and adopt confidential computing? And I have a couple of points. And the first one, I think it's pretty clear that we need to decouple that from the application layer. That means we have existing applications, we have SaaS solutions, we have existing deployments in the cloud. Nobody has the time to refactor anything here. And the second point is this needs to be integrated. That means it needs to fit right into your daily workload, your pipelines, your tooling, your infrastructure as code, for example, everything that you operate with on a daily basis, confidential computing needs to be right in there and integrated. And talking about these DevOps tasks, DevOps solutions, they need confidential computing needs to provide the same functionality. We need to provide the same way of scaling, updating, logging, all of this. It needs to work like it does right now. People are not willing to make any kind of adoptions, any kind of changes to their current workflows. And we need to do that in a way that is having the same or close to the same performance in terms of compute and cost overhead, in terms of I/O, also thinking about accelerators, and all this kind of stuff needs to be provided so people can just go ahead and consume that, and it's almost invisible. And when I say almost invisible, I want to emphasize on the last point, this still needs to be attestable in a meaningful way. That means you really exclude the cloud provider or any other service provider from the TCB, and that means that you can have a clear path from the attestation statement, the attestation you get from the hardware, to the actual components, to the actual source code that's being deployed or that's being used here in your environment. So attestation is what makes this whole thing a thing, and we need to provide the first couple of points to make it usable and then provide meaningful attestation to add a real value. Right. So how do we meet those requirements? I think that's pretty easy. We just put our Kubernetes nodes into confidential VMs, and we're done. Well, of course not. This, of course, adds the functionality of runtime encryption for those Kubernetes nodes. But all of the other requirements I just shown you, they're pretty much unanswered. How is this integrated? How can I attest this? How can I make sense of what's being running there? And how does it fit into my workflow? I don't want to solve this on the application layer or in my deployment over and over again. This should be part of the platform, part of the orchestration layer. So instead, what we want conceptually is one concise confidential context that solves those requirements for me, that provides me with meaningful attestation, and then I can go ahead and deploy my applications inside, and I have the same kind of features, but isolated and protected from the environment. And this concept is what Constellation implements. Constellation is an open source Kubernetes distribution developed and maintained by us here at Edgeless. It essentially wraps your Kubernetes cluster inside a confidential envelope. It isolates it against the infrastructure, protects against infrastructure-based threat, but in the inside, it's a fully fledged Kubernetes that's certified by CNCF. And that comes with a UI or a user experience that fits right into what people are used to in a cloud-native world. So this is the idea, this is the concept. And now Malte is going into the details of what Constellation does to address all those requirements and lift you into a confidential Kubernetes. Please, Malte.
So thank you for the introduction, Moritz. So I really want to explain to you today how we get from individual confidential VMs to like this full confidential cluster. And I think this is quite hard to get to if you just start from these individual VMs. As Moritz showed you before, there's a lot of things that can go wrong. So we really want to start at the bottom. We start out with single confidential virtual machines. And what you have to understand is all of the different CVM implementations have some mechanism to perform measurements. And what this means is you start with one component in your boot chain, and this component will measure and load the next stage in your boot chain, and then execute it. And the important thing to understand here is this measurement can be performed, but it cannot be undone and cannot be tempered. You can only append things. And this means you can always know what has run before your stage is executed. So a confidential VM starts up in the firmware, and the only job of the firmware when it comes to measured boot is just to load up the first stage bootloader and measure it, and then to execute it. And from this first stage bootloader, we load a unified kernel image. This is a great new development that makes measured boot a lot easier. A unified kernel image is basically the Linux kernel. It's an initRD and it's the kernel command line. And all of these components are just packed into a single EFI binary that is all loaded and measured together. So we do not have to be take into account all the individual measurements that we would have otherwise. So after the unified kernel image is loaded, the Linux kernel starts, and it has the initRD. So in this initRD, it will try to mount the root file system. And this root file system is strictly read-only. This means it's completely stateless. And we want to ensure that we actually load the data from this file system that we have specified before. And we do this using dmverity. Dmverity is a Linux kernel feature that allows you to have a file system and a hash tree of the same file system next to it. And whenever you want to read a block, you basically hash this block and then hash everything up into the hash tree, up to a single root hash. And this single root hash allows you very efficiently to check every single block as you read it before you give it to the user land. And in Constellation, this root hash is stored in the kernel command line, and it was already measured in the stage before, so we can trust it. And this means we have read-only file system, we can mount it, and we can trust all the files that are in it. In this file system, we have the Linux user land, and we also have the bootstrapper, which is our component to bootstrap the rest of the process. And next to the root file system, we also have a state partition, which is just where we store the Kubernetes internal state that includes etcd. And this state disk is encrypted and integrity protected. So next, we want to look at how we get from this first booted node to an actual Kubernetes cluster. And after we have booted this first node, it has these boot measurements that I talked about before. And the confidential hardware can then create an attestation statement. And this just means that we have these measurements and we have some additional data. And we use a key that is stored in the hardware to basically sign this. And this can be used for remote attestation. And we do this using attested TLS. And this means the person that sets up the Constellation cluster can perform remote attestation and at the same time get an encrypted channel to this first node. And this ensures that we know three things. We know the node is actually running the confidential hardware that we wanted to run. It is running the correct software that we wanted to run, and it was not yet initialized, so it's fresh. And using this TLS connection, we then send over some information that is required to initialize the cluster. Then the first node will initialize Kubernetes on itself, by its own, and then it will send over the Kubernetes configuration file and some additional information back. And this is how we get to a one-node cluster. So next we want to look at how we can actually scale up this cluster to be bigger and be an actual real Kubernetes cluster. And on the left side, you have the new node that wants to join the cluster, and it goes through the same measured boot chain. And now it will actually perform remote attestation against a service that we deploy inside of the existing cluster. And this ensures that every node that joins the cluster has exactly the same three things that I talked about before. So it's a CVM, it is running the software that we wanted to run, and it was not yet initialized. And if this is the case, then the join service will hand out the required information to join the cluster. So this point I really want to hammer in. We want you to use Constellation just like you would use something like GKE or AKS or EKS. That means we want you to just use the cloud features like load balancing, storage, scaling, managing DNS and certificates. This should all be tightly integrated. And we do this. That means if you have existing deployments, you can just kubectl apply them and they will just work. And we deploy the necessary services for you. The next thing I want to talk about is how do we actually do day two operations. For this, it makes sense to first look at the traditional approaches. So on the one side, we have the on-prem approach. This is just what you would do if you have everything self-managed. You scale up, so that means you put more servers in the rack. You join them into the cluster. You are responsible for updating. You update Kubernetes. This is great for security because you are in control, but it also means it's a lot of manual work. On the other side, we have the current offerings from cloud providers. They can do all of these tasks fully automatically, but you're not in control. And Constellation has an interesting point in the middle, like it strikes a good balance, because we just put all of these day 2 operations inside the cluster. This means the cluster can manage itself, and you as the administrator can declare your desired state. The cluster will just converge to that state. So the whole control plane is confidential, all the services are confidential. So next I want to talk about how the individual nodes talk to the outside world. And here we can see that there are some potential issues where there could be man-in-the-middle attacks or eavesdroppers. And so for the first point, we have encryption in transit. This means if you want to connect to your Kubernetes cluster after it has been set up, you can use a TLS client certificate that was handed to you, and you can also use a CA certificate to actually validate the other side. So you have mutually attested TLS, and you know the identity of the cluster, and the cluster knows your identity. So there's no potential for issues here. The second part is the actual network, the actual traffic between the pods inside your cluster. And for this, I want to take a quick detour and talk about Cilium. In Kubernetes, you always have a container network interface. This is just the implementation that provides connectivity between pods. And Cilium is a really great implementation of this. We use this for multiple reasons. It has eBPF, it's very fast. It also has advanced network functionality, like policy engines that you can use. But more importantly, it provides encryption between the nodes. So Cilium has multiple implementations of this. We use WireGuard. It's really fast. It's really secure. And the default implementation of Cilium at this time has a security issue, a theoretical one, where Cilium might send data unencrypted if it doesn't know about the other party yet. We have worked around this issue, and we have implemented a strict mode that prevents this issue. And we are working on upstreaming this with Cilium. And we will also have a blog post on this soon. So yeah, take a look. The second kind of interaction that the cluster has with the outside world is encryption at rest, so storage. I already talked about our state disk, and this state disk is used to store the Kubernetes internal state, like etcd, on encrypted and integrity protected disks. And it's also really important to point out the keys used for this encryption are always stored in memory in the VM. So if a VM ever goes offline, if you reboot it, it will not be able to decrypt its own state disk. And this is why we implemented a recovery protocol. And in most cases, if a VM reboots, it can just perform remote attestation again with the cluster and just get its encryption keys back. But in cases where the whole cluster goes offline and it cannot talk to any endpoint to do the remote attestation, we also implemented manual recovery using the Constellation CLI. So there's another thing when it comes to storage. And this is Kubernetes workloads actually need more storage. You want to have block storage, and this is very dynamic. You cannot predict what deployments will need storage at what point in time. And we solved this problem using our own CSI plugins. So a CSI plugin is basically just a pod can request block storage, and the cloud provider storage implementation will then provide it. And we wrap the existing CSI plugins from the cloud providers, but we transparently encrypt the block devices. And this already has existing implementations for Azure Disk and Google, and it just works out of the box. You can just use CSI as you would normally do it. The second thing is read-write-many storage. So this is just if you want to share files between pods, or if you want to use S3 compatible object storage. And we can give you this feature by deploying Rook Ceph inside of the cluster, and also using block device encryption. So this is how we come from individual confidential VMs to a confidential cluster that is verifiable and attestable from the outside. We have encrypted storage. We have read-only root file system. We have encryption in transit. We have encryption at rest. So with this, I will give it back to Moritz for the conclusions.
Thank you, Malte. I guess it's a lot of stuff to digest, to comprehend, right? It needs knowledge of both worlds, the cloud native and the confidential computing space. So I want to repeat a point that Malte raises where he said you can just go ahead and do kubectl apply and it will just work. And this is what we're striving for, that you have your usual tooling, you have your existing ways of how to deploy stuff in Kubernetes, and it just should work for confidential Kubernetes as well. But below that, we implement all the stuff that Malte just explained. That's almost invisible. Almost means you can pull it out if you if you want to verify manually, if you want to inspect, if you want to audit, but it's done for you in the background automatically. But everything is always verifiable. And I think that's our philosophy with Constellation. If you want to go ahead and try it out, as I said, it's open source on GitHub. You can just go there, you find easy examples, also the documentation. There are simple steps for deploying your first confidential cluster on your favorite hyperscaler, on a local mode, if you just want to try it out on your local machine, doesn't require any specific hardware, just for you to experiment with that. So yeah, that's my homework for you. Please go ahead, go to GitHub, try it out, and see how it works. That's it. Thank you very much.